Welcome to this overview of our optimization script. We're just going to walk through what we're doing here in code so that you've got a bit of an explanation of why I set up this example to be useful for you to work through. So you're going to have the basic cells you're used to seeing, like getting authenticated to Google in order to be able to work and query the different data sets. We also describe which data sets we'll be using so we can do something like write a query. So we do that writing of a query. We do some normalizing of timestamps. You've seen all of this in the previous demo video. And next we are going to go ahead and create our PACU length of stay information into the data set and search for a day that was really busy. So we see this day here with 6 elective cases and 2 urgent. And so now we've got a busy example day that was greater than 5 cases here on the 17th of April. So we're going to take that date and move forward with it to do a sort of simple optimization to say on that day with our 2 urgent cases, how many elective cases could we have added to keep our probability of going over capacity low? Okay, so we'll start by building a sort of compact PACU simulation that just answers for this set of cases and length of stay value, did the PACU reach or exceed capacity? So that's just setting up a building block we will need later to simulate PACU for a day. Next, we'll do a quick sanity check to make sure that's outputting what we wanted. And we'll move on to go ahead and do the following. We are going to figure out how to choose an elective load that's reasonable with a day that has 2 urgent cases. So we're going to define the urgent cases. We're going to say that this is not under our control. These are just 2 cases we're going to have to take. Then we are going to make the elective cases under our control, and we are going to test across a variable set of how many elective cases we do, and we're going to do a simulation. We're going to keep those urgent cases from this day, the 2 of them, sample the elective cases from our data set to figure out a new elective case load, see what kind of case is it and who did it. And then for each one of those cases, keep the arrival time, but we will resample the length of stay by looking at that empirical experience from the past of how long do people stay in the PACU. We'll run our PACU simulation, and we'll repeat that many times so that our resulting data set, we can say how often did we go over, or our probability of going over given the different elective caseload that we infused into this, okay? And so we're going to split each of the days into that urgent versus elective. We're always going to have the 2 urgent, but we'll have a different set of electives. Now we need to go ahead and estimate that probability of PACU going over full for a given elective load by doing 200 simulations of that elective load that we give it and the urgent cases. So we're setting up a function that's going to return the probability of being full over those 200 simulations. And we'll do a quick test. We can see an example here where the current elective count is 6 and the estimated probability of the PACU being full is 0.78. 0.78 of the cases in that 200 that we did, or 2 of the days in the 200 that we simulated, were over capacity. So this is going to help answer a basic question. So we can take that framework, and what we're going to do with it is set out a small grid search from 3 to 16 elective cases in order to simulate each of those scenarios and find out which ones would have resulted in a high probability of being over capacity. So we'll do that, and we will simulate for 3 elective cases, 4, 6, 12, so on and so forth. And what we're going to find is the answer for the probability of our PACU being full. And so we're seeing between 3 and 6 elective cases, there's a definitely a probability of being full, much lower when we only do 3 electives, and it continues to grow until we hit 9 cases, in which case 100% of our simulations end up over full. So I usually like to build this out into a visual trade-off, and the way that I'm going to do this is say, hey, we probably want to think about this as having some threshold of risk. How comfortable are we with being too full? And so I'm going to start just by setting that as a target probability of 20. Where do I set that? Let's see. Target probability I must have defined here somewhere. Target, I'll just show you an example of how to operate in here. I'm looking for where did I set this target PACU full probability. And so I'm going to highlight that, and you're seeing that it is highlighted back here in this code. And I'm going to just go back through my code to figure out where did I set that. Did I put it all the way at the top when I was making the data set sort of ready to work with? Maybe not. Okay, so I'm going to go ahead and, oh, I did. It's not highlighted, surprisingly. So another way I could have found that same thing is selecting it and going Control F. And now I've got all the different times that this is set. So there we go. We've got a target probability for the PACU being full of 0.25. So that is what we are pulling into our visualization so that we see where that is in reference to our results. And so we may feel differently later on and want to play with that. So let me just go ahead and put that here as well so we can restate what we want the target probability to be to create a different experience. So we had 0.25, and so if I rerun here, I'm going to get the same visual. But this would allow us to do some dynamic planning together and say, you know what, I think we're probably comfortable if we take a target PACU probability full of as high as 0.5. And so it just changes how we view this data. But you're seeing here graphed the results that when we set the elective caseload to 3, here is the probability in our simulations that we go over capacity, quite low, right? I believe you probably saw in the table above, it was something like 6%, 6.5%. And so that's where that value is coming from. And then we evaluate across that range, 4 cases, 5 cases, 6, 7, 8, onward. And so this helps us have a better discussion about how to set that threshold of elective cases. We can say something like if we're willing to accept 50% risk of being over capacity, then we can set the cases as high as 5 elective cases. But knowing, with our decisions, there's variation that's going to cause that to be the case sometimes and not others. So it helps you have a better discussion about that decision, not locking you into a perfect point in time prediction of someone has to make this call and be right about it. So that's the basic work that we're going to do, and we can also build, if we want, a more sort of finish this out, right? So you're seeing here I've just gone and done some basic calculations using those criteria that we've put in case to say that we, in this optimization, have set a risk threshold for the PACU being over capacity to 0.5, which you remember I changed before. It wasn't the case originally, which says that the optimal elective load is 0.4. So let's say, hey, I really want to see, let's get it up a little bit so we can get to 5 elective cases. Then we're going to have to adjust until this gives us, we get that threshold above the result. So we'll change it to something like 0.55 probability of going over. And you see that now we go to the 5 cases, which is now underneath the threshold. But if we put it back to 0.25, we are going to have the threshold actually a little bit below that 4 cases. And so it's going to give us a result to say, with a target risk threshold of this, the optimal elective load is 3 cases. And our probability of going over PACU capacity is 6.5%. So this, you see, I'm quickly transitioning between different concepts here, different thresholds, to make a different decision so that we can have a conversation with our stakeholders about how to make a good choice here, given history and the variation that we expect to be in the process. So there you go. Now you've got a walkthrough of the code that helps us do kind of a simple optimization in Python.